with biologger equipment solutions and technologies.
I promise I won't drain your brains too much more before coffee. So I'm going to take you on a journey today, because right now we're standing here because over 80 years ago somebody had a laboratory accident and they decided to explore it instead of just take it to the sink and rinse it out. So I guess we can be thankful for that because it's led to a significant number of technological advancements, but it's also put us in the situation we're here today. So as we go on this journey, we're going to start talking about the AEC, which is the Aqueous Electrostatic Concentrator for removing PFAS. Sounds like a lot of big words. I guarantee you it is a very simple process. But first we have to talk about a little bit about the history of how we got here. So first, I want to tell you that this technology was designed on the back of a napkin. Why is that important? Well, because all good things come from the back of the napkin, not the front. Secondly, this was originally funded by an SBIR grant from the EPA in answering one of their calls for innovation on PFAS. Okay, so that is something the EPA has watched this technology very closely. We have our first drinking water installation going in New Jersey. They just broke ground and started pouring the footings for the building. And the EPA is working hand in hand with us because the community is part of the technical assistance program. And so far that hasn't gotten cut. We too were a failed experiment because when we got our first hypothesis, what we thought was going to happen didn't happen. And so I'll explain that. And BioLargo engineers are geniuses, but we don't tell them that. You'll see why in a little bit. So, aqueous electrostatic concentration, pretty simple. You have a 3-chambered module. On the outside of the chamber 1, you have an anode. On the outside of chamber 2, you have a cathode. Separating those chambers from the main treatment flow is membrane. So you would have it between chamber 1 and the blue, and you would have it between the blue and chamber 2. As the PFAS come in on an aqueous stream, the PFAS migrate towards the anode. That's what they do. That's nothing new. We know that they migrate towards the anodic side of things. That's why we use anionic resin to take them out when we do ion exchange. So they migrate towards the anode. That electrolytic field enhances that draw. Not a little, by a lot. But what happens is it gets caught on that membrane. It fuses there. You can't get it off. When we started looking at this, and this is where I call it a failed experiment, when we started doing this process, we expected that all of that PFAS was going to end up concentrated in chamber 1. We did our testing. It wasn't there, but it wasn't in the treated water stream. So now we're playing hide and seek with the PFAS. Where'd it go? What we found when we dissolved the active surface of that membrane was that all of the PFAS was stuck to the membrane. Okay. We figured out that if you calculate it out, you can treat 1 million gallons of water with 70 parts per trillion PFAS on 12 grams of membrane with this system. So it's very high capacity. But we did our work in stages. So our first goal was to create something that was low energy. We wanted to create something that was high capacity, but we wanted to be that efficient collector. Because what has happened as we've watched this journey is we've got great collectors for long chain, but we struggled with the short chain. So we wanted to be an efficient collector first. Then, once we got that collection down, then we would look at the destruction process. So when we first started doing our testing, we did like everybody else did. We started on clean water, because that's where you start. Nobody with a new technology wants to start with dirty water right off. First you start looking at spiked RO water, then you start looking at actual water. So when we started doing our actual experiments, this was several years ago. So when we first started, the goal was 70 parts per trillion. So we decided that, well, let's concentrate it up first. So we took and we started with RO water, then we went to RO concentrate. And we started using water where we were treating the RO concentrate. The goal was 70 parts per trillion, so we stopped where everybody else needed us to stop, because nobody wants to pay for more treatment than they actually need. Then we started we were contacted by other communities, we were contacted by some government agencies, and we started testing additional water. So if you look at the New Mexico water, I can't tell you where that water is, but I can tell you it's the most brackish water in the United States and comes from a government agency, and you can probably figure it out from there. The Kansas water was an interesting challenge for us because that water was highly contaminated with TCE. It was off the edge of an Air Force base. And it was a plume that was actually heading towards a drinking water plume that would start impacting a town. So they sent us water, and they said, we just want to get it below 70 parts per trillion. And so you can see we stopped when we got it below 70. Any of these could have been taken to non-detect, as we figured out later on. So New Jersey, groundwater. Wisconsin, groundwater. Minnesota is groundwater. The blue is actually going towards potable. So we had to hit a potable standard for that state. And in New Jersey, I can tell you that's not always an easy task because some of their numbers are lower than that federal EPA numbers. And they also end up with a lot of short chains that aren't necessarily on the regulated list right now. So then we looked at Minnesota, which was just outside of a landfill. We handled that pretty well. Again, we had some RO concentrate in Illinois. That one was a little bit more of a challenge as it was mining water. So there was all kinds of high mineral content in there. It was a little bit worse than seawater actually to deal with. But as we started dealing with the Minnesota water, it struck something in our engineers' brains. Again, remember I said our engineers are geniuses. And they said, why can't we do this with leachate? So we started testing leachate. And what you see there in gray was our first test on leachate. Now, that was Florida leachate. Florida leachate is nice. Florida leachate isn't as highly concentrated. We have now had some West Coast leachate come to us, and I said, I asked for leachate, people, not sludge. But we decided that we needed to collect. So as I said, we started with that removal and concentration of the PFAS because we wanted it to be concentrated. Well, as I also said when we started to play hide and seek, we had to figure out where the PFAS was. Well, we also figured out that we could strip the active surface off those membranes. That created a lot less waste. We didn't have to worry about getting rid of the whole module. We didn't have to worry about even getting rid of the whole membrane surface. We just needed to get rid of the active surface of the membrane. So we actually patented getting the active surface off of membranes when they have PFAS. So then we started looking at destruction, and one of the things that we have found with destruction, and remember I said we started this over a long path, is that when you start talking about destruction, you have to make sure you're breaking the CF bond, not the carbon-carbon bonds. Because it's fairly easy, especially on the carbolic acids, to break a carbon-carbon bond. It's fairly easy to take that long chain and turn it into a short chain. And a lot of times, depending on what you're breaking it into, it won't get caught. Because if you're breaking it into 2C4s and you're not testing for PFBA, you may not pick it up. Or you might get a C5, but you're not picking up the C3 that you now created. So there's still a lot in the destruction process that we aren't seeing, which is why going towards 1621 is where people are trying to. And right now, 1621 is the method the government uses to verify complete destruction. But what we figured out is that by doing this the way that we did and then following our process with a new type of electrooxidation, that hits a contact point of 5,000 degrees, we could break the CF bonds, we could create inert salts. So what ended up happening is in a system where you would have 40,000 pounds of carbon, we would end up producing less than 1 pound of waste that had to be destroyed, and we could take that and turn it into inert salts. So that seemed like a pretty good idea to us. So then we started looking at how could we take this into that leachate, because drinking water has traditional treatments that work well. And no matter how many innovative treatments that you bring out, there is still going to be a strong foothold for carbon and ion exchange in drinking water. It's what people are comfortable with. You know, it's like trying to get somebody who is a, diehard Ford lover to change to a Mercedes. It takes time. Once you get there, you realize, hey, this is kind of nice. But it still takes time to change that mindset. So let's look towards leachate. With leachate, you come up with some challenges because we all know leachate's a lot more nasty than drinking water is. So we decided we had to do some pretreatment, and that's where we started some innovation again. Because our chemists looked at the pretreatment step and said, well, if we do the pretreatment where we have to drop some of these nasties out, basically dropping some of our dissolved solids out and things like that, we can take a step where we use a different type of electrocoagulation. Well, that electrocoagulation, now you're ending up with a solid. So does the PFAS stay in the solid, or does the PFAS stay in the liquid? Well, our chemists found a way to keep it in the liquid. So unlike biosolids, where it is going, the PFAS likes to stay with the solid because of all the organics it can bind to, here we're taking it into the liquid. Well, then we have to do a little bit of VOC reduction if it's truly nasty. Now, if it's just a slight amount, we don't have to do that step. In a lot of cases where it's already been treated by a microbiological step, we can actually get rid of some of this stuff. Then we run it through our AEC. And what we found is that we're getting 99.9% removal in some cases, sometimes to non-detect, of long chains, of short chains, and we just got our testing back on ultra shorts. We have been working with the University of Tennessee, outfitting them to be able to do ultra short testing. And we just got our data back, and we have been able to remove 99.4 to 99.9% of all of the ultra shorts, including TFA. So we run it through this process. The beautiful thing about that is it's a straight through process. It runs in batch, yes, but we're not running the same group in batch over and over again. We can pretty much set it up so that we're running a batch straight through, it's treated. Running a batch straight through, it's treated. It's not until that we hit that saturation point on that membrane that we have to move to the destruction step. So it's a lot faster process. We don't need days, we don't need weeks to deal with the leachate. I need 6 to 12 hours. So in our first testing, we found out that we could remove, after an ultrabiological process, not quite as concentrated, we could remove 98% or better. Why is that one so low? Well, what happens is when you're not as concentrated and a little bit is left over, your percentage of removal goes down, not up. So that's why it looks like that. Because in a lot of cases, we'll be looking at, when you look at the numbers, we'll be looking at 60% removal or 70% removal of, say, a certain type of ultra short. But in reality, we took it to non-detect. It's just that the minimum detection limit of the test is so high that you don't know where you were after that. On raw leachate, we got greater than 99.8% on that particular raw leachate. That one was a stronger leachate that wasn't Florida. And then what we also found, somebody asked us to test if we could destroy foam fractionation fomate. And we were, with this system, able to destroy the fomate at greater than 99.6%. So what does that really mean in numbers? Well, it means that we've had concentrations coming in over 10,000, and we can take them down to, 7.5. We've had, total PFAS coming in over 500,000 parts per trillion. We can take it down. The latest test that we're running now, the last two that came in are in the part per million range. All of these samples, again, could be taken down to non-detect if somebody wanted to. A lot of times there's no reason to take them down that far. It's just more energy and more operational costs. So we can actually bring it down that far. One of the interesting things that we found with all of this is that as we were testing, in some cases where you get an increase in the PFBA because you are breaking a carbon-carbon bond, we were not getting that. We were just getting full destruction. But as you take a case study, it's not just about what you can do, because yes, it's great to be able to do it at a lab scale, but the question is when you take it up to an actual scale, what's the operational cost going to do? What are the disposal costs going to do? How is it economically going to impact something? Because if it's great on paper, but the cost is so astronomical that it doesn't pay to go any farther, then what you've got is a great lab scale toy. So what we did is we started looking at comparing our systems, both on the drinking water side and on the wastewater side, to the most common ones in the industry. And rather than go out to each individual location and say, hey, how much did it cost you, or how much did it cost you? We started where everybody else is getting their numbers, and we started looking at the EPA's numbers, because they're the ones that are going to set the guidances on what do you have to have. Now, in listening to some other presentations a few weeks ago, I found out that the carbon numbers that we're using, that the EPA uses, is fairly low for poundage compared to what is actually being used in the field. One study that I saw 4 weeks ago at a conference had this number up at 750,000 pounds for 2.5 million gallons a day. So what it really looks like is if you're dealing with 2.5 million gallons a day of drinking water, you're going to have, in this case, 540,000 pounds of carbon. When that carbon is spent, you have a choice. Or when you start channeling, you have a choice. Are you going to take it out and reactivate it? Or are you going to just completely take it out and replace it? If you're going to just take it out completely and replace it, right now carbon's going for $3.50 a pound. You have to add $2 a pound minimum transport on that, because thanks to the CERCLA law that we heard about the first day, transport for PFAS-laden material will be around $2 a pound, because it is now a hazardous material for transport. You can't get around that. That is a CERCLA regulated law, and right now it's what they're going with. Nobody knows what the future is going to hold. But right now the waste companies are looking at that going, yep, we're going to have to charge about $2 a pound for transport minimum. Then you're looking at somewhere around $3 a pound for destruction. So all in, when you're looking at this, the estimated carbon replacement costs about $3.3 million plus destruction. We said, okay, what is it going to cost for us? For that same system for us, we were at about $310,000. But did it hold with leachate? That was the question. So we started doing some comparisons, and I thank Ian Cooper from his SWANA presentation for this slide, because it made my life a lot easier. If you start looking at leachate, this kind of gave an all-in comparison on some of the most common leachate treatments and where they stood cost-wise. And so adding ours in there, you're looking at anywhere between $525,000 per year. Ours is electricity cost. and a little bit of membrane replacement. So for the same system, we were somewhere between 27 and 31,000 per year. So that gave us the decision that yes, it was okay for us to move forward commercially. So all in, where we're at with our case studies now is that we are now in the process of taking in leachate and testing more for actual sites that we're able to go into a commercial model and hopefully give another option that's a little bit more cost effective. The key features to this is that we're going through full destruction. So we're not kicking the can down the road, as I like to call it, on putting it into a carbon and then having that carbon go to a landfill, because we don't know what the future regulations are going to hold. If the current regional screening levels stay the same as they are, we could turn every landfill into a Superfund site the minute they want to close it. That means once it's a Superfund site, polluters pay. There is no, that's the little key feature that nobody talks about, is that under RCRA and CERCLA, polluters pay. So if you've put something into that landfill in a large quantity, they will come back to the large quantity depositors and they will say, okay, everybody pony up, we need to clean up this Superfund site. We're seeing it across the country. We're seeing it, people have seen it in Florida where there was a fire and somebody bought the land that there was a fire on years back. And they're coming after not only the current landowner, but everybody that's been on that land since for the cleanup costs. So it really is something where we have to look to the future and we have to say, okay, can we find destruction methods, whether that be high temperature thermal, whether that be supercritical water oxidation, whether that be, new technologies that come up like ours, where we're destroying the PFAS rather than depositing them elsewhere. So with that, I am actually going to take questions. I had one more slide in here and I actually took it out because it's a marketing slide that actually shows that it looks like we created a black box. And I don't believe that there is any black box in treating water, wastewater, or leachate. Everything is dependent on that chemistry. There will be room for everybody in the industry because everybody in the industry is going to be needed for us to tackle this problem. Because there is not one company that we all deal with that could handle every drinking water or wastewater plant in the country. So with that, I'll take questions. Anybody? Bueller? Or y'all just need more coffee? Uh-oh.
Thank you, Tanya. Pat Stanford from Coviana. On one of your slides, you showed after the AEC that you had a brine concentrate coming out of it as well as the pure water. I think that both of those are PFAS-free, but could you explain that a little bit?
Sure. When we use we tend to treat large systems. We'll put an RO in front of it and we'll treat the brine. So what you saw on the slide was actually brine concentrate from an RO, where we actually treat it after an RO. It just cuts down on the number of modules needed. So that brine coming in will actually be treated for PFAS, and then we will give that usable water back in the design of the system. In the case where we're not using the AEC for PFAS removal, there are cases where we will actually use it for chloride removal. It could actually be used for nitrate removal if you wanted to. Then we will actually have a concentrate coming off of that chamber for the ion that we're actually going to take out. So in that case, those side chambers will still be PFAS free because everything is on that membrane.
So if it will do nitrate removal, could it also do ammonia removal?
Most likely, yeah. It's possible. We haven't tested it for that, but It will, I mean, because it is based on an electrolytic process, all of your ions are going to move towards their polarization. So you could, and in theory, you could treat for any ion that you're trying to pull out, and it'll end up in the side stream. Now, we go across a membrane. We don't go through the membrane. That's important to understand. The ions will go through the membrane, but all of the water goes across the membrane, and so the ions are pulled out by the electrical process. So we're not hindered by needing absolute clean water. We're not hindered by other, competing ions to the PFAS. We're not hindered by organics per se. So we have tested this system and been able to take lagoon water in. We have been able to test and take in surface water. We have been able to take secondary effluent from a wastewater plant. So it's because we're going across the membrane, it's a lot more forgiving. Anything else?
Any other questions? Okay, can we give a hand to our speakers, please? Excellent group, and I think we can adjourn and hit the refreshment area a few minutes early. So thanks for attending.